So we left off on this example 2 problem. They were trying to represent and show why the language WW is not context-free by using the context-free pumping lemma. We asked what string would be good to pick, and we identified that A to the M, B to the M, A to the M, B to the M would be a great pick, because we know that A to the M, B to the M has some nice qualities with it that help you to be able to force things in certain places, which is nice. And then repeating that allows any change that you make to the first half to not affect the second half, which is bad for the language. Any change you make to the second half won't affect the first half, which makes it not in the language. Anytime that you repeat A's and B's within the first half or the second half, you're going to end up with something that is not in the language. So you have lots of tools at your disposal to work with in the proof. So we broke this down into cases. We said that the possibilities where they would pick a VXY that was only A's, A's followed by B's, only B's, or B's followed by A's. So that was the 4 cases that we needed to show. So to do this, we need to find a particular I such that if V and Y are pumped, and remember that we don't get to choose where V and Y are, we have to be able to show it for any particular V or Y that is chosen within that category. So it's nice for the ones that are all A's or all B's, because we know that V and Y have to be all A's or all B's respectively. But it gets harder when we have to think about A's followed by B's or B's followed by A's, because we don't know if V is all A's and Y is all B's, or V is A's and B's, Y is all B's, V is all A's, Y is A's and B's. We have all of those to consider as part of our argument, because we don't know where in that string of A's and B's we have the V and the Y. So we need to make arguments for all of that. If we choose I equals 0, we're going to be taking out some of those things. So the only difficult argument, and it's not even that difficult anymore, if you have all A's and all B's, or sorry, you have a string of A's and B's for VXY, and you remove either an A or a B or multiple A's and B's from that. If you compare that first half of the string to the second half of the string, then you will see that they're not the same string. They're not it's not WW. You've made modifications to the first W, but not the second W, or modifications to the second W, but not the first W. So that becomes your argument that this language can't be context-free in that way. So you just have to break it down into a big tree of all of the possibilities here, and then 2 of these, the A's followed by B's and B's followed by A's, those break down into further cases of where those are chosen, but the argument for all of those stays the same. If you remove any of them from the language, then you're messing with either the first W or the second W in WW and not the other, which means that the result won't be in the language. Does that make sense? Kind of summarizing what we did last time, how we ended up to that result, the intuition behind that. But here's kind of what we talked about here, but in slide words. A visual for this. We know that VXY, the length of VXY, has to be less than or equal to M. So this is now broken down where we see segments of length M, 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 and M. So the length of the start of V up to the end of Y can only be up to M characters long. So it's only ever going to be this size or smaller, and you can slide this across the entire string. So you can see how now you get the choice of all A's, all B's, some A's and B's, or some B's and A's. So we don't get to place where this slider is. So we have to make cases for wherever player 1 places this slider. They get the choice of the size of the slider and the location of the slider. They can mess with V, they can mess with X, they can mess with Y, but the entire length can't be longer than M. and it can be anywhere in the string. So because of that, that's why we need all those cases. Questions? What can I help with? What can I go over? Yeah.
Yesterday during the lecture, you had, I don't remember exactly, but you had a W and a W. And then you had, let's see, V, you had VXY, like the length of VXY in one of them. And then you said like, oh, you can't do this because now they're two separate things. But like, how are we, I thought the whole point was that we had to somehow augment or do something to one of them to make sure that that you didn't have the same W to kind of like contradict what is being said about the language. And so that was, I was confused on that because it didn't quite make sense when you're just like, oh yeah, like we're supposed to manipulate something here, but now they're two different things and now we can't do anything. So that didn't quite make sense yesterday.
No longer remember what I was doing.
Oh, yeah.
Does anyone remember enough to help recreate the example so that I can try to figure out what I was saying?
I'm just asking all this.
Yeah, we can try to recreate it in office hours, and then whatever the result of that happens to be, I'll share it with the rest of the class probably tomorrow.
Sure.
Unless anybody else has a place to ground me. I'll go back and watch my own lecture video. Ugh, can't stand watching myself. But that's true for everybody though. Okay, next example. How about a to the n factorial? So we want to show that a to the n factorial is not context free. So first, as always, we need some kind of string form. Probably something that has to do with this concept of m. Then we need to solve things for every possible location for VXY. Luckily with this one, it shouldn't be terribly complicated. Has to be all A's, right? What are we picking for our string?
It was A to M factorial.
Seems like a great idea. What's your intuition? What leads you there?
Because if you're pumping anything in that M range, it's not gonna trickle down through the factorial section.
Yeah, you know for sure that VXY has to be, if you have m factorial, then you have m times m minus one times m minus two times m minus three times dot 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 times three times two times one m's. We don't know where in that the VXY is being pumped, but we know things like the total length of V and Y can't possibly be more than M, right? So what does that let us do? What value of I can we use such that we know we're not going to generate a new factorial when we pump V and Y I times? Zero is a good answer. Why? What's the intuition that works with zero? Yeah, we're taking away A's, and we need to get to m minus one factorial, right? So we need to remove m of them. So you can start messing with this concept. If we take out the pumped sections, V and Y, we can represent that as an expression, m factorial minus k plus L, where k is the number of A's in V and L is the number of A's in Y. This can only possibly be in the language if that expression happens to be some factorial. Does that make sense? You're basically setting I to zero, removing V and Y from the string. So all you're left with is UXZ. So we can set this up by saying m factorial minus this sum k plus L needs to be equal to some factorial. We'll call it j factorial for some j. If this is context free, that needs to be the case. How do we know that k plus L is less than m? That's true by the pumping lemma constraint, right? We talked about how the length of this has to be less than m. So it has to be greater than m minus one factorial. Has to be. There's no factorial in between m minus one factorial and m factorial. So there's no possible j that can satisfy the above expression. That's our contradiction. People buy this?
So I have a concern with this, like.
Yeah,
If you don't, like in, what we have up there, we don't have set numbers, we're working like. N can be anything, and I, like, in. Could that create a chance that you could stumble into a situation where. You moved it down a factorial, so like. You produce some, by taking some away, you could have stumbled into, let's say, n was 5, you stumble into 8 to 4 factorial.
we're arguing that for any k and L that is valid because of the pumping lemma constraint, that no matter what you instantiate m as, you can't possibly reach m minus one factorial. So you could never reach 4 factorial from 5 factorial. You could not remove enough of that. V and Y could not be that big of a chunk of the string because then it's larger than m, which isn't allowed.
Is that n factorial minus? Yeah, or should it be m?
Which one?
On the last line.
Oh, the very last m minus, yeah, m factorial minus k plus L. Yeah, there's this right here. This should be m factorial here. My bad. Yep. Does that make sense? We know that the number of A's in V and Y, so K plus L has to be less than M. So we can't remove M of them to get to M minus 1 factorial. Can't do it. So we can be a little bit clever with these proofs too. They don't just necessarily involve that same exact form. You can use other logic and you can look at, if we're going to use factorial, we can use the definition of factorial in our argument. Questions on this example?
I'm still sort of confused on like, when we're getting rid of the pumping from. So B and Y. right?
Yeah,
So like, if we were to go through, let's say M was. And we set I equal to 0, would that mean if we were just not to pump anything at all, that would mean that our string would be like 0, like nothing, and be empty? Because-
you can't pump nothing at all. Because this has to be an infinite context-free language. One of the constraints is that the size of B plus Y has to be greater than or equal to 1. So we have to pump something. If we had a string of size 2, then at least one of those would have to be pumped, would have to be B or have to be Y or have to be both. If it's not an infinite context-free language, then it's regular. If it's a finite language, then it's regular. In which case it is context-free. Does that make sense? Does that answer the question? Or is there, can I justify some more?
It's sort of, I think it makes enough sense. I'm still kind of like working through.
Yeah,
I have a question, but I'm not sure how to word it. Can L, are those?
the number of A's in B and Y.
Oh, there it is. I'm not around.
It's okay. This kind of takes a while to dissect, to really just look at it and see intuitively why it works, which is why I'm not super pressured to move ahead super quickly. Because I see a lot of people staring and digesting, which is good. Reason about this in your head to come to the reasoning as to why this is correct. Because it's very much worth the time spent to do so. This is basically the equivalent of setting I to 0. We're removing an amount of A's equal to V plus Y. We're calling this K plus L to represent the number of A's. If you take a particular factorial and you take away some number, such that the sum of the number that you take away has to be less than M. We would have to take away M, or rather, we'd have to divide by M to get to M minus 1 factorial, right? We need to remove a factor of M. If you're going to subtract up to M rather than divide out up to M, there is no way that you're going to reach the associated number of M's to get down to M minus 1 factorial. You're not going to get there.
Can you repeat that last line?
I think the problem I'm having is I'm like, I'm trying to just do it by 1 and 2, but like 2 factorial, which is 2, 1 factorial, just be 1, it's not like you subtract 1, that gave you 2 factorial, 1 factorial.
Right.
So I think that's fine. Move that forward.
Gotcha. So you're saying there's a case down there, there's a single case.
Yes, a single
where that would
case
work.
where it's not working.
Note that this would have to work for all factorials in order for this to work. So you basically
So
just
it's
need,
I've got that.
It's good to be thinking about those low cases and say, does it work for every case? How are we doing? We ready for our last example? Might be worth staring at this a little bit at some point. We can come back to it as well. But the last one we're gonna do is a strange one. A to the n, b to the j, such that n equals j squared. So we have the square of the number of b's in terms of number of a's. Yep. Number of b squared number of a's. What are we thinking for our string?
A to the m squared, b to the m, or wait, what's that? Yeah,
I like it. What leads you to that intuition?
well, I mean, it's kind of just because of the definition of the language, it's just easy to plug in and like that.
Yeah. Why do we think this might help us? It is very easy to plug in from the definition, but moving beyond that, what's the intuition of how this will break down or how this can lead us to a pumping lemma solution? Yeah,
No matter what sections you finish, kind of breaking that and squared like a relation. Cause like if you have the. So basically the two sections, you have A's and B's, if you have the. What is it, the VXY in on the left side, then you're just gonna explode B's and they'll fall off, or A's will get out of line. Have on the right side, you get too many B's.
yep.
If you divide between the two, you're increasing on equal amounts, which throws out the shot.
We also have the opportunity to put more A's than B's, but have both A's and B's, or more B's than A's and have some. So would it be possible to make the alignment perfect such that when you expand it, basically you're getting continuously n squared, like you're consistently producing the square on the left of what you're producing on the right? Is that possible? How could we go show that? Yeah, it's a different order, right? One is going to increase linearly, one is going to increase quadratically. So now we need a way to go show that relationship. That's a very good intuition, and I would probably accept that intuition on a homework or on an exam as a good enough proof. Does that make sense to everybody else? Where the linear is coming from, where the quadratic is coming from? We're drawing out anyway. How am I going to visualize this? So we have. To keep this in the language, we have some number of A's and some number of B's, such that this left-hand side is the square of this right-hand side. Probably want to make this a little bit shorter. So the left-hand side is the square of the right-hand side. So this needs to grow quadratically. This needs to grow with proportion to the square of this. So if we're going to continue to add to both sides, we need to add according to the square of this side, which is going to explode faster than this does. But what we're doing when we do this, when we're pumping this process times, if we're gonna use I equals 2, we're gonna put the same number, and I equals 3, the same number, so you produce a linear equation. By doing that, like let's say I was 10, whatever we had dedicated was the portion of this that's gonna get pumped, and the portion of this that's going to get pumped. As I goes higher and higher, this expands linearly and this expands linearly. Even if this is higher than this, they're still expanding linearly. Whereas this needs to expand at the square of this to stay in the language. And when you have different orders like that, we know that for large i's, they don't behave the same. They're different classes of running times or functions for a reason. Because they grow very differently. So if that intuitively makes sense, let's take a look at how you might show this in an actual proof form. Again, I mentioned if you do this on homework or an exam that just goes to that level of detail, that's not a proof, but it is enough intuition that anyone with a brain would buy your argument. Okay, so we need to break this down into cases, all A's, some A's and some B's, or all B's, and exactly as Arthur said, the A's case and the B's case is exactly, it's pretty straightforward. If we're only adding A's and we're only adding B's, then we obviously are going to break the square relationship between the number of A's and the number of B's. So just set I equal to 0, the resulting string will not be in the language because we've broken that square relationship. Argument for some A's and some B's is a bit more difficult. If V is made up of all A's and Y is made up of all B's, we can check the size of them. If the size of V is 0, we can use I equals 0 and that will break it. It kind of turns into the all B's case. If the size of Y is 0, use I equals 0, that will turn it into the all A's case, which you've already shown. But the tough case is if neither the length of V or the length of Y is 0, which means that we need to come up with some mathematical expression that is going to show that the quadratic nature of what needs to happen is different from the linear nature of what is going to happen. So we can show this mathematically by setting this up as an expression. We know that if we're going to take away, we know that the y's all come from this right-hand side of the expression. We have m b's, and we know y is made up of all b's. So we started with m b's, and we're going to take away the length of y b's. And to represent the number of a's, we just have to square that, right? If we square that, we should get the number of a's that we need to have taken away. That has to be less than or equal to m minus 1 squared. FOIL it out if you need to, you'll find that that's the case, because the length of y has to be greater than or equal to 1. So if we're subtracting 1 or more than 1, then that's going to end up being smaller. The left-hand side will be smaller than the right-hand side. Right? This value, length of y, we know because of the pumping limit constraint that the length of Vy has to be greater than or equal to 1. And we also know that neither of these are 0, because if they were, we would have been in this trivial case from before. So both of these have to be non-zero. So it's going to be, in fact, we can even say it's greater than 1 in this case. So this probably can be strictly less than, because this is going to be greater than 1. So this left-hand side must be less than this right-hand side. So we can set up the expression like that. Manipulate from here. FOIL out the right side, we get m squared minus 2m plus 1. And we now know that this is basically m squared minus the size of v, right? Because when we're taking away the a's, we can replace this m squared, which was the original number of a's, with this expression that has to be the number of a's that we're taking away. So we know that m minus the length of y squared is less than m squared minus v. So the number of a's that we're going to have is fewer than we need them to be in the language. Therefore, the result can't be an L. Does this argument make sense? We started with the definition for the number of b's that there have to be, right? This is the number of b's. You square it to get to the number of a's that we need to get rid of. So this needs to be equal. Right? The number, when we take away y and then we square this whole thing, that needs to represent the number of a's that go away. In order to keep this quadratic. So we set it less than or equal to m minus 1 squared, FOIL it out, and we see that it's strictly less than m squared minus the length of v, which is the number of a's that we would need to remove. Or sorry, it's the number of a's that we're actually removing. So since these are not equal, there's a strictly less than in there. Then we know this cannot be, this cannot stay. So this is the mathematical argument for why this is the case. The computer science argument is probably just their different orders. Therefore, they're not going to grow at the same rate. Therefore, there will be some I for which they are not the same, because they're not growing at the same rate. Questions on this proof?
Not that far of the proof down.
So this just represents the number of a's that we're removing. So when we are going to take away, so we're setting I equal to 0, which means we need to remove the length of b a's and the length of y b's. So we can say the number of a's that we're removing is just m minus whatever that length is. The number of a's that we're removing in terms of y has to be the square of that, right? If we're removing length of y b's, then we need to remove the square of that number of a's. So this is the number of b's that we're removing, this is the number of a's that we're removing. We can bound this by something that we know to be true. FOIL that. And then we see that that is less than this number of a's that we need to remove anyway. This is linear. This is quadratic. So here we've actually shown how the number of a's, when you square the number of b's that get removed, the number of a's that get removed is linear rather than quadratic. And because those aren't the same, then we can show that that breaks it. So I just wanted to show kind of the more technical side of these proofs. So we have counters for every possible strategy now, yeah.
I'm just thinking, is 2m plus not, sorry, is 2m plus 1 not exactly equal to v?
It's less, it's definitely less than. Is it not? What are your thoughts?
Well, my thoughts were when you go from like x squared to x plus 1 squared, you're adding 2x minus 1.
Mhm.
I don't know, I'm having a hard time like just comparing the two in my head, I'm not sure.
That is a good point. The issue is we're not adding one to a square. The issue is that we are trying to compare in general, when we square this, we would need to have some square term in the length of b. This was the original number of them, so this represents what we subtract from them when we square this. And one is linear, one is quadratic.
Okay, yeah.
I think that will get you there.
Yeah, I was trying to set if that statement was true.
Yeah, that's an interesting point, though. It's a very interesting
Well,
point.
because V would, or the length of V would be equal to 2m minus 1, not plus 1, so when you
Yeah.
subtract the larger one.
Yeah.
Slightly less.
Slightly, yep. So the reason this works is that we divided this into cases. We looked at all A's and all B's. We proved those. We looked at some A's and some B's, and we were able to divide that down into cases where we looked at all of those cases. So we needed to make arguments for all of those cases to be able to show that this language is not context-free. We just had to keep breaking it down into more and more cases until we covered all of the cases. And that's just what's necessary to go through a proof like this. You can't short circuit it, you can't stop early and show it for some of it. You need to actually go through the whole process. Yeah,
So the last part of that, you said that we'll always be able to find an I where that's not, or it breaks it, if there's
Yeah.
a contradiction, so can we just say kind of informally that there's always gonna be an I, just because they're different growth rates?
if you have an argument for why there will exist an I, then yes.
In this case specifically, is it enough to say that there's always gonna be an I? That-
I think if you make the argument that a quadratic expression grows faster than a linear expression, then there will exist some I such that there's a difference.
That was more of just like a.
That would be good enough to me. That's a more intuitive argument, but I think as a computer scientist, we don't need the technical argument all of the time.
It was more of like a. How formal do we have to get with it?
Yeah. For these more difficult ones, that would definitely be good enough. But this is also more difficult than anything I would throw in an exam. Okay, there's one last thing to talk about, and we're not going to dive into this too deeply. I present it mostly for context. So don't worry about memorizing the pumping lemma for linear languages, but it's a very important result that we use in compilers. So we saw the difference between linear and nonlinear context-free grammars. The distinction can also be made between languages. A language is linear if there exists a linear context-free grammar for it. And do we remember what I meant by linear, or what we mean by linear? There's at most one non-terminal in each production. So we're only turning a variable at most into one other variable, which means that we can parse it linearly. We're never having to branch and take a look at multiple non-terminals and resolve multiple non-terminals. We're only ever going to be doing it once, which means that it's linear. You can kind of draw it on a line. We have this non-terminal phrase in terms of this non-terminal phrase, in terms of this non-terminal phrase, in terms of this non-terminal. So you just have to go down once and back up, kind of a single recursive chain to be able to determine whether or not something's in the language. So we would want to also express a pumping lemma for the way to express whether or not a language can be expressed as a linear context-free grammar. So we call that a linear language. So every linear language is context-free. Not every context-free language is linear. If you can make a nonlinear grammar for a language, that doesn't necessarily mean that it's not linear. There may be a linear context-free grammar for it. You just found an equivalent grammar that is not linear. In order to prove something is not linear, we need to prove that we can't generate a linear context-free grammar for it. To be able to prove that, we need a very related but slightly different pumping lemma to the context-free grammar pumping lemma. So what does it actually look like? And again, I'm mostly presenting this for context. There will not be homework problems asking you to do this. There will not be exam questions asking you to do this. This is just to show that there is a very similar pumping lemma to the context-free pumping lemma for linear languages. We say, let L be an infinite linear language. We can again find an M such that any string W that's in the language with the length of W greater than or equal to M, looks identical so far, can be decomposed once again into W equals UV X, Y, Z with the associated constraints. We now have to include U because it's linear. We can attach it to the left side like before, like we did with regular languages where we said the XY had to appear within the first M characters. Now we can say UVYZ has to be less than or equal to M. The pumping length again has to be greater than or equal to 1. And those are the two constraints that we will use to be able to say that UV to the I X, Y to the I Z is in a language for all I. There's one really interesting thing about this. We said we can dock it on the left side because of U, this length has to be less than or equal to M. Note that this Z must also, this is the dock on the right side of the string, also has to be less than or equal to M. So it means that the entirety of the string minus the X, that is just the non-terminal going to the terminal representation at the very end of the string. That's the only thing that can push this string to be longer than M. Intriguing. So what does it imply? The pumped substrings V and Y must be within M characters of the left and right ends of the string. So since U is the start, Z is the end, V and Y is what gets pumped. The V has to be within M characters of the left, the Y has to be within M characters of the right. And that restriction makes it very easy to do this kind of pumping lemma, or rather it unlocks a lot more kinds of arguments that you can use. Just like with the regular pumping lemma, we were often using the fact that XY had to occur in the first M characters of the string, and that allowed us to make a lot of easier arguments or simpler arguments for why something wasn't regular. That's very much the case for linear languages as well. The middle string X can be of arbitrary length. There's no restriction to that. And so the logic that you use follows closely to that of the context-free pumping lemma. But again, we have a couple extra things that can help us to create some easier solutions to this. So as mentioned, this is not technically part of the course, but it is an important result for, because we care a lot about things like linear languages when we care about compilers and efficiency. So if there exists a way to represent a context-free grammar as a linear grammar, then we're going to have a significantly easier time parsing it. So we may actually care about this distinction of whether or not a language is linear or not. Questions on that? All right, we're basically done for the day. You all looked a little bit dead today. Do something nice for yourself today. I say that as, my homework is due tomorrow and we have an exam on Friday, but do something nice for yourself.
Do all tomorrow.